morning everyone. Welcome to this another video lecture of discrete math course. Today we're going to talk about algorithms and their complexity analysis. If someone asks you to define an algorithm, then usually people say the algorithm is some kind of a procedure which is going to give me a desired output for a given set of input. So algorithm is basically a set of rules which is required to obtain the expected outcome from a given input, and more precisely we can give the definition of the algorithm as is a finite set of precise instructions for performing a computation or for solving a problem. You can think of many examples where you can write an algorithm to solve those problems. So for example, if I take a list of integers as my input, then if I'm interested in finding the largest integer in that list, that could be my output. And now I can think of putting certain rules or certain precise instructions such that for the given input of list of integers, I can obtain my largest integer in that particular list. Or you can think of another problem where I take a given set A as my input, and my output is to list all possible subsets of that given set A. Whenever you write an algorithm or you write a set of instructions so that you can get an output for a given set of input, there are few properties your algorithm should satisfy, and those properties are written here. The first is your input. So an algorithm should have an input value from a specified set. Then the second is your output. So for the input values, the algorithm should produce the output values from a specified set, and the output values are the solution of your problem. The algorithm should have this correctness property. So an algorithm should produce a correct output values for each set of input values. The fourth property your algorithm should have is finiteness property. An algorithm should produce the output after a finite number of steps for any input. The fifth property your algorithm should have is the effectiveness. So it must be possible to perform each step of the algorithm correctly and in a finite amount of time, so the algorithm should be effective. And the last one and the important one is the generality. So the algorithm should work for all problems of the desired form, and it should be written in a very general way so that in future if you want to extend your algorithm, it should be easy to extend because it was written in a general way. You don't want to re-implement or redo the things from the beginning if you just have to extend your algorithm to solve some other problem which is related to your earlier problem which you have been solving by using that algorithm. When it comes to how to specify an algorithm, then it can be described either in a simple English as a set of instructions to follow, or it can be represented in the form of a pseudocode, where the pseudocode is an intermediate step between an English language description of the steps and a coding of these steps using a programming language. The pseudocode concept is important because by using the pseudocode, the programmer can use the description of an algorithm to construct a program in a particular language. It could be C, C++, Python, MATLAB, Octave, or some other programming language. And pseudocode also helps us in analyzing the time required to solve a problem by using that particular algorithm, independent of the actual programming language burden to implement it. So before doing the actual implementation, we can even compare the time complexity of two different algorithms which is used to solve a same problem, and based on that we can decide which one is the more efficient algorithm to solve that particular problem, and then we can actually implement it. Let us take one example of how to describe an algorithm for finding the maximum value in a finite sequence of integer. And let's suppose I have a list array which is written here in the form of A, which has the element 4, 1, 2, 6, 3, 8 and 10, and the index of my array is starting from 1, 2, 3, 4, 5, 6, 7. So it has a meaning that my array at the index 5 will have the third element. Okay, so how can I describe an algorithm to find the maximum values in this given list of array. So the general logic to describe an algorithm here is you just define a temporary maximum variable and assign your first element of your array as going to be this maximum value 4, and the index of that first element 1 is going to be my index of my maximum element in this array. And then what I do, I start by comparing this from my second element, and my second element in this array is 1, and if I compare 1 with my temporary maximum, then 1 is less than 4, so my temporary maximum is still going to be 4. I'm going to move to the next element, which is 2, and if I compare 2 and 4, 4 is still the maximum number, so then I'm going to move further in my array. The going to be next element is 6, 6 is greater than 4, I'm going to replace this temporary maximum from 4 to 6, and the index of my temporary maximum is now becomes 4 because this is the index here. Then I'm going to move to further in my list. The next element is 3, 3 is less than 6, so my temporary maximum is going to hold. Then it's going to be the next element is 8, then I'm going to replace 6 by 8, and my temporary maximum index going to be 6. Then the next element of this array is 10, and 10 is also greater than 8, so I'm going to replace this 8 by 10, and this index is going to be 7. So by using this logic and by comparing every element of this array, I can obtain the maximum element present in my array, and the maximum element, the output of my algorithm is going to be 10 here, and the index is going to be 7 here. Okay. Now you can describe this the whole logic to compute the maximum element in a given array. It can be performed by following these 3 steps. In the first step, you set the temporary maximum equal to your first integer in the sequence, which we did it here. Then you compare the next integer in the sequence to a temporary maximum, and then if it is larger than your maximum, then set the temporary maximum equal to this integer, and that we performed in by comparing every other element of this list to my temporary maximum number. And then is the last step is going to be repeat those previous steps if there are more integers, otherwise you stop, and when you stop, the output of this problem is going to be 10, and the index with respect to your maximum element is going to be 7. Based on this set of instruction, which is written in a simple English, we can also generate the pseudocode of this algorithm. So my procedure is going to be the maximum, and my list of integer is given here, a1, a2 all the way up to a of n. The types of my input is going to be integers, so this is my input, and this is the type of my input. Okay, this is the name of my procedure, and so the first step, I'm going to assign a temporary maximum, which is going to be the first element of my given list of integer. Then for every element starting from 2 and to the last element n, I'm going to compare the ith element with this temporary maximum element, and if maximum is less than a of I, I'm going to update my maximum to that particular element a of I, and I'm going to return the maximum, which is going to be the largest element present in this list of integer. So you see this is an example of a pseudocode which is written in some kind of a logic formulation, and a programmer can easily read it, and they can implement it in whatever language they want to do the implementation. So that's the beauty about the pseudocode. It represents your set of instruction in a logical way, so that the programmer, whether it comes from a background of C or C++ or MATLAB or Python or Octave, everybody can read that syntax, and then they can analyze the algorithm, and they can decide what data structure they're going to follow, and they can do the implementation in whatever language they prefer. After establishing the concept of algorithms, we want to establish the concept of complexity of the algorithms. So the first question we want to ask for any given algorithm, that how efficient is this algorithm for solving a problem for a given input of a particular size. Okay, that means we are trying to ask two questions here. The first question is, how much time does this algorithm use to solve a problem, and how much computer memory does this algorithm use to solve a problem? Okay, so there's two questions, one related with the time and one related with the computer memory that this algorithm is going to take if they're going to solve a problem for a particular size input. So when we analyze the time the algorithm uses to solve the problem for a given input size, so that means we are studying the time complexity of the problem. And when we analyze the computer memory the algorithm uses to solve the problem for a given particular size input, that means we are trying to study the space complexity of this algorithm. Okay, in this course our focus will be only on time complexity. For the space complexity, we're going to learn this concept in a particular course which is more devoted to algorithms and algorithm designing, which is going to be your course in computer science department. Here you're going to learn only the primary introduction about the concept of complexity, and in particularly about in terms of your set of operation which is related with your time complexity. So before we actually learn how to do the time complexity of the analysis, let's learn about these three cases, which is the best case, worst case, or the average case scenario of your algorithm could be. So let's take an example of you have a list of element which is represented in the form of an array, and the array is represented by A here, which has 1, 2, 3, 4, 5, 6, 7 elements, and then the index of this array, let's suppose the index starts from 0. So 0, 1, 2, 3, 4, 5, 6 is the index of my element which is present in this array. Now I want to write an algorithm for searching an element, and you can do the searching of an element based on the comparison. So I can build three different cases here, and those cases is the representation of my best case, worst case, and the average case which is going to appear in my algorithm. So the best case of your algorithm is you are trying to search a key element which is 5, and the location of 5 which is in your given array is at the starting, so is at the first location. Okay, so what will happen, you take this key element which is 5, you're going to compare with the first element of this array, and just within one comparison you will see that that element is present in your array and your searching is done. Okay, so the minimum number of comparison which you required to solve this particular case, when you are trying to search the first element present in your array, they're going to represent the best case scenario of your algorithm. The second case is going to represent the worst case scenario of your algorithm. So think about certain input which you are trying to search an element in this array, which can give you the maximum number of comparison which you have to use in this algorithm. So you can think, if you are trying to search an element where element is going to be equal to 9, because the 9 is going to present at the last position of this array, then you're going to do the maximum number of comparison just to say whether 9 is present in that list or whether it's not present in the list. Or the second, you can choose an element which is not present in this list, then you're going to compare it with every element which is present in this list. Okay, so with respect to these two scenarios, if you have a list of element 5, 8, 16, 11, 3, 2 and 9, and let's suppose you want to check whether the element 9 or the element 4 is present in that list or not. So you're going to compare with the first element, you're going to compare with the second element, you're going to compare with the third element, fourth element, fifth element, sixth element and the seventh element. So the 7 number of comparison, you're going to do it here. Then only you can decide whether that element is present here or not present here, and this is the maximum number of comparison your algorithm can hold for any input. So this represents the worst case scenario of your algorithm. The last third case is going to be the average case scenario of your algorithm, where the searching element, the key which I'm trying to search, whether it's present in this array or not, it could be all possible elements as an input. So I can think of an input which could be present at the first place. I can think of an input which could be present at the second place, maybe at the third place, maybe at the fourth place, maybe at the fifth place, sixth place, seventh place. Okay, so this represents the average case scenario of my algorithm. But then the challenge here is I have to build this input. Okay, I have to build this input which is going to give me all possible inputs which can be possible to run that particular algorithm. Okay, and that's going to represent the average case scenario of my algorithm. So again, the best case scenario is going to be that particular input which I'm going to pass in my algorithm, which is going to take the minimum number of operations. The worst case is going to be that particular input which is going to take the maximum number of operations, and the average case is going to be all possible inputs which I can think of. They're going to take the average number of operations in my algorithm. Let's suppose I want to count the total number of comparison which I am performing in this particular searching algorithm, and if I take n is my input size of the given array is going to be equal to n, and if we define t of n as a time complexity function based on this input size of the array n, then for this three scenario we can analyze this time complexity function. So in the first scenario, in the best case scenario, my time complexity t of n is going to be equal to 1. I'm just counting the total number of comparison. So for my best case, my searching element is present at the first location. I just compare it only one time, and the total number of comparison, if I have a list of elements or an array size equal to n, then t of n is going to be equal to 1. So that means in terms of the big O and big theta notation, I can say my time complexity with respect to the best case is big O of 1 or big theta of 1. That means it's a case of constant complexity. While for the second case, which represents the worst case scenario of my algorithm, if my size of an array is n and I'm searching an element which is present at the last location, so the total number of comparison which I need to perform here is going to be equal to the size of an array. So in that case, my time complexity function t of n becomes equal to n. So my time complexity function is a linear function here, and for a linear function I can easily prove that t of n is a big O of n, or I can also say t of n is a big theta of n. So in this case, my complexity will be linear. In the last case, which represents the average case scenario of my algorithm, I need to analyze the time complexity when I choose an searching element which could be all possible elements, and those elements could be present at the first location, second location, third location, fourth location, all the way up to the last location in your array, or it may not be present in your array. So you can obtain the time complexity in case of average case is by using this formula, that t of n is going to be equal to the time for all the cases divided by the total number of cases. Okay, so if you start putting the total number of comparison you are performing, so let's suppose if we take the first case when the key element which you are searching is present at the first location, then the total number of comparison you are performing is 1. When the searching element is present at the second position, the total number of comparison is 2. When this present at the third location, the total number of comparison is 3. If you are taking an array of size n, and if the searching element is present at the last location, or if it's not present in your given input, then the total number of comparison you are performing is n. So the total time for all the cases is going to be the sum of all those number, which is 1 plus 2 plus 3 all the way up to n, and then divided by the total number of cases which you are considering in your input to represent your average case scenario. Then you're going to divide everything by n, and we can apply this summation formula here. We know the sum of the first n integers, positive integers, is going to be n times n plus 1 divided by 2, and then divided by this factor of n. This will cancel out, and everything will be equal to n plus 1 divided by 2. So your time complexity for this case, t of n, is going to be equal to n plus 1 divided by 2. Okay, which also have a linear growth, and for this case, for the case of average case scenario, we can also prove that t of n is big O of n and big theta of n. So in this case also we have a linear complexity. Now we have present the best case, worst case, and average case scenario of my algorithm. Now, which cases out of these three cases should be a factor in deciding which algorithm is an efficient algorithm? Then you will agree with me that the best case scenario is not a useful case to analyze the algorithm, because it represents the it doesn't give you any useful information to say whether the algorithm is taking how much time for your particular input. It's giving you the best case scenario, which is not useful from the time complexity analysis point of view. So the only choice which you have is the worst case scenario. You can analyze the algorithm based on that, or you have the average case scenario. You can analyze the algorithm based on that. But if you compare the worst case scenario with the average case scenario, the average case scenario is comes with a burden of choosing all possible inputs. Okay, choosing all possible inputs and then trying to find the time complexity with respect to all possible inputs which is possible in your algorithm is a challenging task. Even sometimes you have to think from a statistical point of view whether you are choosing a proper distribution of your input when you analyze the average case scenario of your algorithm. So this is a average case scenario. In principle you can use to analyze an algorithm, but it's not possible that you can find all possible inputs for a given algorithm in general for all cases. So people usually avoid to analyze the algorithm based on the average case scenario because of the challenge of finding this the proper distribution of your input, which can give you the average case scenario of that algorithm. So the only choice which you have is which is practical and which is mostly useful, and it can be applicable for almost all scenario, is the worst case scenario of your algorithm. And the another point, people prefer the worst case scenario because this gives the worst case, and the time complexity function which you obtained here is basically going to give you an upper bound on your algorithm. So based on that you can decide whether your algorithm is efficient or not. So let me summarize what we did in terms of our time complexity. So to analyze the time complexity of the algorithm, we determine the number of operations such as comparison or the arithmetic operation like addition, multiplication, and we can estimate the time a computer may actually use to solve a problem using the amount of time required to do those kind of basic operations. So we will focus on the worst case time complexity of an algorithm because it provides an upper bound on the number of operations an algorithm uses to solve a problem with the input of a particular size, and it is usually much more difficult to determine the average case time complexity of an algorithm and this is the average number of operation an algorithm uses to solve a problem over all input of a particular size. It's very difficult to obtain the statistical distribution of all those inputs for your practical algorithm. So in practice, we usually analyze the algorithm based on the worst case time complexity scenario. So let's look at the first example, how you do this time complexity of an algorithm. And in this case, we took the example which we have been discussing so far, how to find the maximum element in a finite sequence of integers. So I have the pseudocode of my algorithm, which is written here. The input is going to be the list of integers, and there are integers of size n. So my input size in this algorithm is n. Then I'm performing this set of instruction which is written in this pseudocode. So I can build my time complexity function, which is t of n, which is based on my input size n. So in this pseudocode, I have one for loop here, and then I have one comparison operation inside this for loop here. Okay, so what I can do, I can write this time complexity t of n by using my summation. So this summation starting from I is equal to 2 to n is because of this for loop condition. From I is equal to 2 to n is the for loop, and then inside this for loop I'm doing the one comparison where I'm going to check my index, whether my index I is less than equal to n or not inside that for loop. And then I'm performing one more comparison because of this condition that my temporary maximum is less than your AI element or not. So I have 1 plus 1, 2 comparison inside the for loop, and then I have one comparison outside that for loop just to exit the loop. Okay, so I can write my time complexity t of n is nothing but summation I start from 2 to n, 1 plus 1 inside the bracket where the summation will apply, and plus 1 to exit the for loop. Now if you simplify that, that will be equal to summation I will go from 2 to n, 1 plus 1 is going to be equal to 2, and then 1 is going to be outside that for loop. Now if you just obtain the sum of this term, it's going to be 2 times of n minus 1 and plus of 1, because we are adding 2 starting from 2 to n index, so you're adding 2 n minus 1 times, so it's going to be equal to 2 times of n minus 1, and 1 is going to remain as it is, which if you simplify is going to be 2 of n minus of 1. So here you have obtained that the time complexity of this maximum algorithm is going to be equal to 2 of n minus of 1, which shows me a linear growth. And I can say, or I can prove here, that t of n is big O of n, as well as I can say that t of n is big theta of n. Okay, so the complexity of this problem is a linear complexity, or you will say it's a linear time complexity. Okay, so that has a meaning that if your array of size n will increase, then the time taken by this algorithm is going to increase with a linear growth with respect to its input size. Now we're going to study the time complexity of the sorting algorithms. And sorting means you want to sort the element of a list. Either you want to put them in a increasing or decreasing order, or you want to put them in a certain numerical order or alphabetical order, and so on. Okay, and sorting problem is important in computer science because a non-trivial percentage of all computing resources are devoted to sorting, and different kind of list, especially application involving large database of information that need to be presented in a particular order. It could be a customer ID, it could be a part number, or the bank account information, or something else. So the another amazing thing about the sorting is There are many different algorithms is available in computer science to do the sorting, and their advantages and disadvantages, this has been studied extensively. And sorting algorithm are useful concept to illustrate the basic notions of the computer science in general. So our first sorting algorithm is bubble sort. In a bubble sort, makes multiple passes through the list, and every pair of the elements that are found to be out of order, they're going to be interchanged. So my input here is going to be a list of element, and my output is going to be the list of element in an increasing order. And I will do this bubble sort by making the multiple passes throughout this list, and I just check two pair of the elements in my list, and if I see that they are not following my particular order, increasing order, and they are out of order, then I'm going to interchange them. Okay, let's learn this algorithm through an example. So my bubble sort algorithm can be explained with the help of this figure. So let's suppose I have a list of element which is 3, 2, 4, 1 and 5, and I can perform this algorithm, and this, if it contain n elements, then I required n minus 1 number of passes. And in each passes I will do two operations. One is my interchange. So my interchange is defined by arrow at both sides. And then I have a pair, and my pair operation if they are in a correct order. So I'm going to keep them as it is. Okay. So if you start from this list of element 3, 2, 4, 1 and 5 in your first pass, you're going to compare the first two elements 3 and 2. And since 3 is bigger than 2 and you want to put this list in increasing order, so you're going to interchange them. Okay, once you do the interchange, then this list of element will change to this one, which is 2, 3, 4, 1 and 5. Then we're going to compare the next two element 3 and 4, and 3 and 4, they are already in a increasing order, so you perform the pairing operation. They are in the correct order, you don't do anything. Okay, then you compare the next two element 4 and 1, and 4 and 1, because 4 is bigger than 1, so you're going to perform the interchange operation, and then again you do the comparison between 4 and 5, and 5 is bigger than 4, so you don't do anything. So after the first pass, you will notice that the last entry in my list of element, it has been fixed at the last place. So the last place will hold the largest element in my given list of elements. So you can say that after the first pass, the largest element has been put into the correct position, and the 5 is going to be at this fifth place. Then I'm going to perform the second pass, and in the second pass I'm going to compare the first two elements 2 and 3, and since they are in a proper order, I don't do anything. Then I'm going to compare 3 and 1, and I'm going to interchange them because 3 is greater than 1. And then I'm going to compare 3 and 4, and since they are in a increasing order, I'm going to keep them as it is. So after my second pass, you will see the last two elements in my list that has been fixed at the correct position. So 4 and 5 is going to be at the correct position now. Then you do the same thing in the third pass. In the third pass, you compare the first two elements 2 and 1. You put them in a increasing order, so you do the interchange operation. There's going to be 1, 2 and 3. You're going to compare 2 and 3, and they are already in a correct order, so you keep them as it is. So after this third pass, the last three elements of this list has been fixed at the correct position. And then you do the last fourth pass, and in the fourth pass you just compare the first two elements, and if they are in the correct order, you keep them as it is, and if you have to interchange, you interchange them. But after this fourth pass, if you pass a input array of size 5, then you will see your output, which is the list of element in an increasing order after the fourth pass. So the general rule is, if you have a list of array of n elements, you have to perform n minus one number of passes to put that list in an increasing order. Okay. So this bubble sort procedure you can also represent in the form of a pseudocode, where my procedure is a bubble sort. I'm going to pass a list of elements, and I have n number of elements here. Their types are real numbers, and my size is going to be n greater than equal to 2. I can perform this algorithm with the help of two for loop. One is on the index I, starting from 1 to n minus 1, because I required n minus 1 number of passes. So they are representing your n minus 1 number of passes. And then inside that I have another for loop where my index j will go from 1 to n minus I, and there I'm going to check whether my two consecutive elements a of j and a of j plus 1, they are in increasing order or not. If they are in increasing order, I will keep them as it is. If they are not in increasing order, I'm going to interchange their position, and I'm going to repeat this procedure, and after n minus 1 number of passes, I will see my output as a list of element, but now they are in a increasing order. When it comes to the worst case time complexity of this bubble sort algorithm in terms of the number of comparison, so then if we notice here for input size n, we can write our time complexity function t of n with the help of this expression, where the first summation I from 1 to n minus 1 is for a loop 1. So my first for loop is here, and I will say is a loop 1, and I'm going to, inside that loop, I'm going to do one comparison to check the condition in the for loop whether my index I is less than equal to n minus 1 or not. Okay, and this is for loop 1, and then I'm doing this one comparison to exit the for loop 1. Okay, then you go to the second loop, and this second summation is with respect to this second loop, and I have index j will go from j equal to 1 to n minus I, and inside this loop I'm going to perform two comparison. So the two comparison, one to check the condition, check whether j is going to be less than equal to n minus I, and then one more comparison just to check whether a of j is greater than a of j plus 1 or not. Okay, so I have to check two comparison here, one to increment my for loop here, and one to check this condition whether I have to apply the interchange operation or not. So 1 plus 1, two comparison I am making inside this for loop, and then one comparison I am making to exit that loop. So exit loop 2. So I can represent my time complexity function in the form of this expression, which if I simplify, then I can write the solution of this problem as t of n is going to be equal to summation I go from 1 to n minus 1, and then 1 plus the summation j will go from 1 to n minus I, 2 plus 1, and then I have a plus 1 outside the summation, which if I simplify from my summations or sums trick is going to be equal to 1 plus, I'm adding 2 starting from index j is equal to 1 to n minus I, so it's going to be 2 times n minus I, and then plus 1, and then 1 outside this summation, which is basically equal to summation of I will go from 1 to n minus I, then you have a 2 of n plus of 2 minus 2 of I, and then plus of 1, which is equal to summation I will go from 1 to n minus 1 of 2 of n plus 2 minus summation I will go from 1 to n minus 1 of I, 2 will go here, and plus of 1, okay, which will be equal to 2n plus 1, 2n plus 2 is going to add from I is equal to 1 to n minus 1, so it's going to be 2n plus 2 multiply with n minus 1 minus 2 times of then you can apply your summation formula here. It's going to be equal to 2 times of n minus 1 times n divided by 2 and plus of 1, which will be equal to, if you simplify, so which will be equal to n square plus n minus of 1. So from here I will get that my time complexity t of n is going to be equal to n square plus n minus 1. And for this function I can easily prove from my growth of the function idea of big O notation and Big-Theta notation that t of n is big O of n square, or you can also prove that t of n is Big-Theta of n square. So we proved here that the time complexity of this bubble sort algorithm is going to be big O of n square or Big-Theta of n square. That means it's going to have a quadratic time complexity. Our next algorithm which we're going to study is the insertion sort. So if you remember, in the bubble sort algorithm we were doing the sorting from lower to upper side. In the insertion sort we will do the sorting from left to right. So for a given list of elements, let's suppose 3, 2, 4, 1 and 5. So what we do, we start our comparing our element, the second element with the first element, and if they are not in a specific increasing order, we're going to interchange their position. So in the first pass, since I'm comparing 3 and 2, so I'm going to interchange and I'm going to put them in a increasing order. So the first two positions are interchanged, and after the first pass the first two elements are going to be in the increasing order. Then my index is going to move from 2 to 4, and in this case from the second element to the third element. So in this case my third element will be here 4. So my fourth is going to compare with the first element 2 and with the second element 3. So when I compare 4 with the first element, so 4 is bigger than 2, so the place of 4 is going to remain as it is. When I'm going to compare 4 with 3, the 4 is bigger than 3, so the place of 4 is going to remain as it is. So in the second pass, when my index is on this element 4, then the third element is going to remain on its position. So after this pass, my first 2, 3 and 4, they're going to be in the increasing order, and the rest of the element I have not visited so far. Then my index after this second step is going to shift on the fourth element, and my fourth element is 1. I'm going to compare this 1 with the first element, which is 2, and I know that 1 is smaller than 2, so I'm going to do the interchange. And once I do the interchange, okay, so if I take 2, 3, 4, 1 and 5, and I'm on this index 4th, where the element is 1 is present. When I'm comparing 1 with the first element 2, then I know 1 is smaller than 2, so I need to do the interchange. Okay, so this is going to be here. Okay, then 2 will go there, agree, but then we have to do one more thing other than searching which one is the smaller and bigger. We have to do the kind of a movement. So kind of movement what we are doing, instead of putting 1 at the first location first, what I will do, I will make this space empty. This 5 will remain as it is, and I will shift this 2 3 4 because 2 3 4 is already in an increasing order to this side. So this will be 4, this will be 3, this will be 2. So this operation is my movement operation. Okay, once I've done this movement operation, then this place is empty. Now I can replace my 1 here. Okay, so that's going to be the third step of this procedure. At the last step, when my index is on the last element 5, I'm going to compare 5 with 1, 5 with 2, 5 with 3, 5 with 4, and I'm going to remain I'm going to keep this 5 at the last position, and this is going to be the output of my insertion sort algorithm. So the insertion sort algorithm begins with the second element. It compares the second element with the first element and put it before the first element if it is not larger. That's the case happening here. Okay, you compare 2 with 3. So 2 and 3 are not in a increasing order. So you're going to replace 2 by 3. So this is going to be the output of this step. The third element is put into the correct position among the first 3 elements, and this you do just by putting your index at this third location. So my element here is 4. I'm going to compare 4 with 2, and 4 is bigger than 2, and 4 is going to compare with 3. 4 is bigger than 3, so 4 is going to remain at the same position. Okay, and then I established this fact in this insertion algorithm that on each kth pass, the first k plus 1 element is put in the correct position. Okay, that means they are in the increasing order, which you can notice here that in the first step or first pass, the first 2 element was put in the specific order. In the second pass, the first 3 element was put in the specific order. In the third pass, the first 4th element was put in a increasing order, and in the last step, which was the 4th pass, the first 5 element was put in a increasing order. So if we have a list of array of with n elements, so the total number of pass which you required is n minus 1. Okay, so the pseudocode of this algorithm can be represented in the form of this algorithm, where you have the procedure insertion sort. Your input is the list of n element starting from a1 to a of n. The types of the element which you are entering as an input is the real number, and the size of your input is greater than or equal to 2. You can solve this problem by using one for loop and one while loop and for loop inside the first for loop. You're going to start comparing your element from second element up to the last element. You put an index to your first element. You're going to compare. This is going to represent this loop 1 is going to represent your total number of passes, and they're going to be n minus 1 number of passes in performing this insertion sort. Then I'm going to check whether my jth element is going to be greater than to my ith element or not, when I index is always going to start from 1. This I can do by using this while loop, and I'm going to fix that element if they satisfy that condition to an m. And then for this for loop, this is going to make the shifting, or is going to make the movement. Okay, in my algorithm, while this while loop is going to give me the index, okay, you can say it's going to give me the searching index for interchange. Okay, and after following those steps, I will get the output of my algorithm, which is now is going to be a list of element in an increasing order. Okay, so you can try a few example and run this pseudocode and see if you get the correct answer. Okay. When it comes to the time complexity, then for a given list of n elements, that means my input size is n. I can write my time complexity function t of n with the help of my counting my number of comparison inside this pseudocode of my insertion sort algorithm. So I'm performing one comparison here inside this for loop. I'm doing one comparison here in the while loop, and I'm doing one comparison here in the for loop. And this while loop and for loop is the nested loop inside my the first for loop. So for the terminology to explain this time complexity, I'm saying this is going to be my for loop 1, this is going to be my for loop 2nd, and this is going to be my while loop. Okay, and I'm doing one comparison in loop 1, one comparison in loop 2, and one comparison in your while conditional statement. Then by counting all those number of comparison, I can write my time complexity in the form of this expression, where this first summation is the representation of my first for loop. The index is going from j is equal to 2 to n, so j is equal to 2 to n, and inside that for loop I am performing this first comparison to check the index whether j is less than equal to n or not. Okay, so if you check this comparison, this is the one comparison operation you are performing under that. Then since the while and for loop are going to be inside the first for loop, then you are also doing one comparison for the while loop, where you are doing a of j is greater than a of I or not. Okay, just to check this comparison. And then inside that first for loop, you are having the second for loop, where the second for loop index will go from k is equal to 0 to, it should be j minus I minus 1. But since the index I is starting from 1, and in the worst case scenario my I will be 1, so my upper index in this case becomes 2, j minus 2. Okay, so I'm doing one operation here to compare this condition for my second for loop, which is the k is going to be less than equal to j minus I minus 1, this condition. And then this 1 is because of to exit the loop second, and at the end this 1 is to exit your loop first. Okay, so this way I can represent the time complexity function with respect to this pseudocode of insertion sort algorithm. So the next thing, to get the big O and big theta estimate on this time complexity function, we need to simplify it. And to simplify means we can use those summations which we learned in our last chapter. So we can write this time complexity function is going to be j starting from 2 to n, and then inside that is going to be 1 plus summation I will start from 1 to j of 1, and then summation k will start from 0 to j minus 2, and then 1 plus 1 and plus 1. Okay, which if you simplify, that will be equal to summation j will go from 2 to n. Inside the bracket you will have 1 plus this summation will be equal to the index is going from 1 to j, and you are adding 1 those many number of times, so it's going to be equal to j plus this summation you can replace by the value, since the index k will go from 0 to j minus 2, and you are adding 1 with that many number of times, so it's going to be equal to j minus 2 and then plus 1, because your index is starting from 0, and then plus 1 and then plus 1. Okay, which is going to be equal to summation j is going to be equal to 2 to n. This expression is going to be a j plus j is going to be 2 of j, plus then you have a plus 1 here, plus 1 here is going to cancel this one, so you're going to have a plus 1 here, and then it's going to be plus here. Okay, which you can represent as 2 times of summation j will go from 2 to n of j, plus summation j will go from 2 to n of 1 and plus 1 to exit that loop. This will be equal to This you can apply your sum of the first n integer is going to be n times n plus 1 divided by 2 minus of 1 plus the 1 is adding that many number of times, so is going to be n minus 1 and plus of 1. So this you can write as a, if you simplify, it's going to be n times n plus 1 minus 2 divided by 2 multiply by 2 plus n, and this will cancel out. This will cancel out, so you get n times n plus 1 minus of 2 plus of n, which will be equal to n square plus of n minus of 2 plus of n, and which will be equal to n square plus 2 of n minus of 2. So in that case, we obtain our time complexity T of n is going to be equal to n square plus 2 of n minus of 2. Okay. So it's going to be a quadratic polynomial, and then we can use our result from the big O estimate and big theta estimate that we can conclude that T of n is big O of n square and T of n is big theta of n square. Okay. So again, the complexity of this problem is quadratic. So in this chapter, we learn how to apply this concept of summations and big O and big theta estimation in analyzing the time complexity of sorting algorithms. And for our case of bubble sort and insertion sort, in both cases we proved that the time complexity is going to be quadratic. So although there exists some algorithm which has a time complexity better than this quadratic time complexity, which we proved in the case of bubble sort and insertion sort algorithm here. Like for the example of merge sort algorithm, you can prove that the complexity of the algorithm is order of n. So the idea of studying the time complexity and algorithms here is not to study every algorithm, just to give you an idea how you can use this concept in analyzing your algorithm from the mathematical point of view. And I hope in future you will use this concept in analyzing the searching, sorting, and some other kind of algorithms in this Kickmat course, as well as in computer science when you're going to learn about algorithms and designing of the algorithms. When it comes to understanding the complexity of the algorithms, then the common use terminology are given in this table. When we say the big theta of 1 is a constant complexity algorithm, when we prove is a big theta of log n is a logarithmic complexity, big theta of n is a linear complexity, big theta of n log n is a linear arithmetic complexity, big theta of n to the power n b, which is a polynomial complexity, and if you prove that is big theta of b to the power n, where b is greater than 1, is a exponential complexity, and big theta of n factorial is your factorial complexity. If you compare all those algorithms based on your number of operations which you used, and if you just plot them with respect to your increased value of n, and with respect to log n log n square to the power n factorial, then you see after n is equal to 10 in this part of your table, okay, they're going to take more than 10 to the power 100 years, okay, to execute those many number of operations when your problem size becomes larger than 10. Okay, so because of this reason, you prefer the algorithm which has a time complexity may be up to quadratic, but the best case scenario, you want to have an algorithm which is of these three kind: log of n, and n times log of n. Okay, so you can divide the whole classification into two parts. So up to n to the power b, you will have an algorithm which is a kind of a polynomial complexity algorithm. And for those algorithms which going to take a big theta of b to the power n, or big theta of n factorial, which is exponential or a factorial complexity, those we put in a class of a non-polynomial complexity algorithm. Okay, so remember, in case of a non-polynomial complexity algorithm, because of as your input size grows, then they are not easy to execute. Okay, because they're going to take forever, so they are not the preferred algorithms in solving your problem. And in your course in discrete math, second course in math 307, as well as in your algorithm designing, you're going to see many examples of those exponential and factorial complexity algorithms. So based on the complexity of the problem, we can have three different kind of problems. And first is your tractable problem. So tractable problems are those problems where there exists a polynomial time algorithm to solve them, and these problems are said to be belongs to the class of P. Okay. The another problem is your intractable problem, and that means if there does not exist a polynomial time algorithm to solve those problems, those you call as a intractable problem. And there is another class of problem is a unsolvable problem. That means no algorithm exists to solve them, and there's an example of a halting Turing problem, which comes in the category of unsolvable problem. Okay. So based on that, we can also define is a class of NP. So those problems where the solution can be checked in a polynomial time, but no polynomial time algorithm has been found for finding a solution to problems in this class, those you call as a class NP problems. While you have another class, class NP complete. So if you find a polynomial time algorithm for one member of this class, then it is believed that it can be used to solve all problem in that class NP, and those you put them in a classification of class NP complete. So this P versus NP complexity problem is a major problem in the area of computer science. It asks whether every problem whose solution can be quickly verified by a computer can also be quickly solved by the computer or not. So there is two general belief. One is says that P is going to be equal to N of P, and the another belief is P is not going to be equal to N of P, where P is my class of all those problems which can be solved by the polynomial time algorithm, which usually give an upper bound, which in the form of some kind of a polynomial expression. And we have studied this bubble sort and insertion sort. Those are the example of those kind of a polynomial time algorithms. While NP and NP complete, NP can only be solved by the non-deterministic polynomial time, and such as determining whether two graphs are isomorphic or not. Another is your NP complete, so there is no fast solution known for those kind of problems, and your knapsack problem is going to be part of that, which you're going to study in your Math 307 course, as well as in your algorithm designing course. Your NP hard is going to be NP hard problem, which is as hard to solve as the hardest problem in your NP class. And one example of that NP hard problem is your traveling salesman problem, which you're going to study in your Math 307 course. When we study the P versus NP problem, then the first question you will ask whether the P is going to be equal to NP or not. So that means are there problems whose solution can be checked in a polynomial time but cannot be solved in a polynomial time. And note that just because no one has found a polynomial time algorithm is different from proving that the problem cannot be solved by a polynomial time algorithm. The another theory was that if a polynomial time algorithm for any problem in the NP complete class were found, then that algorithm could be used to obtain a polynomial time algorithm for every problem in the NP class. And it is generally believed that P is not going to be equal to n of p, since no one has been able to find a polynomial time algorithm for any of the problems in the NP complete class. So finally, in conclusion, the problem of P versus NP remains one of the most famous unsolved problems in mathematics, including the area of theoretical computer science, and the Clay Mathematical Institute has offered a $1 million prize who's going to come up with the solution of this problem, whether P is going to be equal to n of P or whether P is not going to be equal to n of P. And this is the major problem in the area of mathematics as well as computer science.